One of the biggest values that enthalpy has for chemists is that it allows us to measure heat either given off or absorbed in a chemical reaction. And so that's why you learned about enthalpy in your general chemistry class, and why we're coming back to the topic again. So just because we have this wonderful relationship that delta H is equal to Q, and H is a state function, that gives us a lot of power in predicting and knowing what enthalpies of reactions will be. Just as a reminder, something you probably already know, but and something we've already talked about, if delta H is negative, that's what we call an exothermic reaction. And by our sign convention, that means heat is leaving our system and heating up the surroundings. So that's why we have an increase in temperature in the surroundings when there's an exothermic reaction. If delta H is positive, we call that an endothermic reaction. That means heat is coming from the surroundings and going into the system, which cools down the surroundings. So we can have either of those possible. Now, if we have some chemical reaction, just again, a reminder, something you already know, but that the change in enthalpy for a reaction is equal to the enthalpy of the products minus the enthalpy of the reactants. And we can use the fact that H is a state function to find different pathways to get the value that we want for a chemical reaction. And this can let us even get enthalpies for reactions we either haven't experimentally measured or that are very difficult to do experimentally. And so enthalpies are tabulated for a lot of different things. And we'll get to the idea of enthalpies of formation in the next video. But we can use our known values to find new values. So, for example, let's say we have the oxidation of carbon, graphite, to CO2. And maybe we can only do this one step at a time with the reaction setup we have. So we take our carbon plus oxygen, and it goes to carbon monoxide first. And the enthalpy of this reaction is minus 110.5 kilojoules. And we could consider then carbon monoxide getting oxidized again to go to CO2. And that has an enthalpy equal to minus 283.0 kilojoules. And so if we know both of these, then we can find the enthalpy for the overall reaction of carbon plus O2 going to CO2 by just adding together H1 and H2, right? These two enthalpies over here, we just add those together. This should be review. You're probably familiar with this idea from general chemistry. So the enthalpy for reaction 3 is just the sum of these two, or negative 393.5 kilojoules. One other thing to remember about reactions is that if we flip the reaction around, do the opposite, our endothermic process will become an exothermic process and vice versa. All we do is change the sign. So if we were, say, looking at CO2 decomposing into carbon plus oxygen, will have the opposite sign. It'll be positive 393.5 kilojoules. You'll get the chance to practice with this in more complicated situations and longer reaction chains, both in class and on your homework. But this is just a reminder of things that you've learned before in general chemistry.